Hi, everybody. Welcome to Lecture 7. Woohoo! Lecture 7, where we get to go dabble now in Orgoland in three-dimensional space. Now we're going to go play and figure out how do these organic molecules really look in three-dimensional space. So put on your three-dimensional space hat and let's go play. Again, I thought it's been a long time since I've seen all of you. So I put all of you in my actual, there's my class. Yes. Have you decided which fuzzy mole you actually are? Okay. We could label them. Who's the blue one? Who's the brown one? All right. This is going to be a lot of fun looking at molecules in three-dimensional space. What's most important, though, is if you have something to build molecules with. So hopefully you have your molecular model kit. If you don't, get your toothpicks and marshmallows out. Find something to help you visualize molecules in three-dimensional space. So at the last lecture, I asked if you could please build butene, specifically 2-butene, which is this structure on the slide here. So please try to build that. And what I'd love for all of you to do at this point is hold it up and let's see how many of you built, which one of you, how many of you built the molecule on the left where the two methyl groups are on the same side of the double bond? And notice for the model kits, the double bonds are these stretchy bonds here. This is the only way you can make a double bond in the model kit. And the two methyls are on the same side. Okay. And then now a show of hands. How many of you created the other 2-butene, where the two methyls are on opposite sides of that double bond? Okay. Now feel free to take the one you have and try just to rotate that middle bond to turn it into the other one. You can't. That double bond does not rotate. This is what makes these two molecules very, very unique and will now cause us to completely change the way we look at organic chemistry, because I could create a molecule like these two that have the exact same molecular formula. Notice the formula up there, exactly the same molecular formula. That would show up exactly the same in the IR, the mass spec, you know, all our tests, yet I could create two different ones. I could create the one on the left and the one on the right. And therefore, welcome to the new world where it is not just, you know, structural isomers we're going to be looking at, but now we're going to play with molecules that could create stereoisomers, where the pieces of the molecule could be in different regions of space. And therefore, this is a whole new world called stereochemistry. And we're going to start playing around with these stereoisomers, specifically these alkenes, and try to understand a little bit more about their chemistry. Okay. So first off, both of these are both called 2-butene. There's nothing wrong with that. The problem is, though, that we know now I can't just rotate one to create the other. Doesn't do it. And so these two actually need two different names. So part of today's lecture will be about how do we name these two. Starting off, we're going to give them these names to begin with. And I do mean to begin with. That in just a couple slides, we're going to have to change these names. But these are very familiar names, very common names, and you'll hear these names being used often. So I'd be remiss if I did not show you these names. When you have the two biggest groups, in this case, it's pretty easy to spy that the two little hydrogens are on the bottom of this double bond. And the two biggest groups are these methyls at the top. When they're on the same side of the double bond, we would call that cis. As soon as you break the bonds, move them, and switch them to create the two methyls on opposite sides, this wouldn't be known as trans 2-butene. So you're going to hear this terminology. And again, these two molecules are completely different in everything they do because I can't freely rotate them. That the cis 2-butene has different melting points and different boiling points than the trans 2-butene. Okay. These, again, are called stereoisomers of one another, not structural isomers, because they are built the same way, same type of bonds, just putting the bonds in different regions of space to one another. Stereoisomers. And since it takes, as we proved back in our commercial a few lectures ago, our commercial break where we do a twist and shout, that it takes 60 kilocalories per mole to break this double bond, and room temperature is only 20 kilocalories per mole. We can't interconvert between these two different stereoisomers very easily. So we have a world now that has existing in it different molecules based solely on space. Ooh, I feel like I should have some space music coming in here. So to give you a sense of importance, so you understand the torture you're about to go through, the fun you're about to go through and why it's important, is to come back to this idea that if I have stereoisomers that have different properties, then they obviously are going to have some different chemical reactions. And some reactions that are in our body and the world around us will only occur with one of these two stereoisomers, for example, not the other one. And some reactions will only make one stereoisomer when two are possible. So this could have a big role, and does have a big role, in our biological systems. For example, this drug, which has this beautiful long IUPAC name, okay? This drug actually has this double bond here, and the chloride, and this big chain here, kind of to give you perspective, they're kind of on the same side, okay? So this double bond and this stereoisomer is the actual antipsychotic drug that is mentioned above here, this chlorpromethazine. I can't say that very well. Chlorpromethazine. All right, sorry. I'm not good at drug names. I'm good at the other ones, though. The IUPAC name is perfect. It's just too long. So this is an antipsychotic drug. But if I were to flip that chain over and put it on the other side, on the bottom of this alkene, and get it away from the chlorine benzene ring, this no longer has any antipsychotic effects, and therefore would be a disaster if I were to give somebody who needed an antipsychotic drug, if I needed that drug and I gave them this form of it. So you can see even our bodies have a way of recognizing one stereoisomer over another, and that plays a huge role in the drugs we take. Also, the foods you eat. Welcome to cis and trans. Now they actually relate to something you might have heard about. Trans fatty acids. Trans fatty acids are awful for us. They raise our LDL, our bad cholesterol. They get rid of the good cholesterol, HDL. They're not good for us to ingest. And huge laws are going into effect to stop fast food restaurants from using trans fatty acids. Now you know what the trans part is for. If you look at the structure, you can see that the two hydrogens in this trans unsaturated fatty acid are on opposite sides of each other, which means the two biggest groups are on opposite sides. That's why it's called a trans fat. As opposed to oleic acid, which has its double bond and puts the two largest groups on the same side. And this is an unsaturated fat that's healthier for us, but we'll see in a moment is less likely to occur. And last but not least, if you get rid of any of these unsaturation, you get rid of it all and you make it saturated, then you have what are known as saturated fats, which are also bad for us. So don't do trans fatty acids. Cis fatty acids unsaturated are pretty good. They're all right for us. That's the kind we'd want, but they're also harder to keep around. And let's go look into that. So why are cis isomers a little more uncomfortable, a little harder to make and stay than the trans fatty acids? And it has to do with something called steric strain. So let's be clear about this. Here is my molecule with my two biggest methyls, just like the picture on the slide over here, showing the two methyls right on top. The issue is that as they spin around, these models don't fully express it, But these two hydrogens here, as it's shown on the slide, they actually could bump into each other. Ouch! Ugh, that's not good. Atoms bumping into each other. No, that would be bad. They're all full of electron clouds on each side. So bumping into each other is bad. And so what this molecule will do is try to relieve that collision to make sure that these atoms don't approach too closely. They will repel each other and push each other away, and therefore cause some strain, because that takes some energy to push them away from each other. And therefore we call this steric strain to distort the bonds and allow for a lack of collisions. We pull them apart and relieve it with a little steric strain. So this requires a little energy and makes it a little harder for this cis alkene to form, because it is just not as happy as if it was in the trans conformation. Notice the two methyl groups will not bump into each other on a trans conformation, one top, one bottom. Okay, so no steric strain here in the trans alkene. But trans saturated, unsaturated fats are worse, harder to break down in our bodies, and that's why they're not as good for us. Kind of cool. All right. Now, how do you spy a cis or trans stereoisomer is really important. If I were just to give you these simple molecules like 2-butene, it's pretty obvious these are the two biggest groups. They're going to bump into each other as opposed to these two, and they're cis to one another. Now, I'm about to tell you about cis and trans isomers, but again, I want to warn you, this cis and trans nomenclature is only temporary. We are going to have to get rid of it because we use it for other molecules that are not alkenes, as I'll show you in a minute. There can be some cis and trans molecules without alkenes. So I think we'll come up with a very special nomenclature for just alkenes. Actually, I didn't think of it. 3 dead chemists came up with it, and we'll show you what they are in a second. To understand that you even have the possibility, though, that you better start worrying about using these 3 dead chemist rules that I'm about to show you to determine cis or trans for an alkene, it's really important that you don't just default that every alkene is cis or trans. For example, here is an alkene that I made with my model kit, has 2 hydrogens on the end. And so looking at this one, according to this rule, these 2 groups must be different on one end of the alkene to be able to be what is known as a stereocenter. Okay, and that stereocenter is going to help me create a stereoisomer of a cis or a trans alkene. So what if the 2 groups on the end are exactly the same, like these 2 hydrogens? Then there is no stereocenter here, because I could turn this molecule over and you couldn't tell which hydrogen was the higher priority or bigger piece or smaller piece. There is no bigger or smaller if they're exactly the same. So sometimes our alkenes don't have this unique stereocenter, and therefore you do not have to worry about naming them cis or trans. So keep an eye out for that. We need 2 different groups on both sides of the alkene. That way I can distinguish what's a bigger group versus a smaller group. Okay? So let's try to come up with a strategy on how to rank these, because here's a different alkene. And how do you know if the methyl is bigger than the Cl or the F? Where do you want them? How do I name them? Who is the highest priority, meaning heaviest piece on each end of the alkene, to see if they are on the same side or opposite sides. So here they come. More nomenclature, new nomenclature, woohoo! And here comes the 3 dead chemist rules that I call them, but really Kahn-Ingold Prelog sequence rules. are very hard for me to remember, so I just name them the 3 dead chemist rules. And this is probably out of jealousy that I don't have any rules named after me. That, you know, I wish one of these was the Kahn-Ingold-Doe sequence rules, but since I don't have a rule named after me yet, we'll use these Kahn-Ingold pre-log sequence rules. And these rules are going to help us identify the highest priority, the heaviest pieces on each end of the alkene, so I can tell if the biggest groups are on the same side or opposite sides. So, rule number 1. Let's start with this basics. I'm always looking at only one side, the same side of the carbon-carbon double bond, to try to distinguish which atom on that one side has a higher priority, is heavier. And therefore, I'm going to go to the higher atomic number. I'm not going to look at the whole CH3. I'm looking at this carbon versus this hydrogen. Okay? And only those two. And looking at only those two, I know that the carbon has a higher priority than the hydrogen. It's not the CH3 group. So let's be really clear. These 3 dead chemist rules are going to be very, very strict in that I'm just looking at atoms attached to each other, not groups. And so that makes perfect sense on the other side. Then you can see the Cl has a higher atomic number than the fluoride, and so it will be the higher priority than F. So in the old days, meaning last slide, we would have called this cis. In the new days, where the Kahn-Ingold pre-log sequence rules take place, aka 3 dead chemist rules, we have new nomenclature. Because these gentlemen were German, they actually named things that had things on the same side, like this one, both on the same side. And I'm going to butcher this because I don't know German. The Zusammen, meaning together, means the highest priorities are on the same side. Oh, my, you hear that? I'm already even using a really funny, stupid little way to remember this. If you want to know if your alkene is Z and has this notation with its designation, Z means that the 2 highest priority groups on each side are on the same side. Get it? Same side? Okay. All right. All right. Okay. It doesn't take much to make me happy. So, same side, Zusammen. So what happens if they were on opposite sides? We have to have a German name for that too, and that is Intergegen. Sorry, I totally butchered that as well, but that means opposite sides in German. And so if these 2 highest priorities on each side turned out to be on the opposite sides from one another, we would label them as E, and that alkene would have that distinction. So now you can look at your 2 butenes, and you can tell me that the one with the methyls on the same side is Z, and with the 2 methyls on opposite sides is E. And so we would label these as Z2-butene and E2-butene to let the reader know where do we want to stick the methyl groups. Okay? So it now bleeds into the rest of our nomenclature. We love nomenclature. All right. A reminder, why did we have to go to E and Z, and why couldn't we just stick with cis and trans? Nick, I was doing so great with cis and trans, and then you just threw me this curveball with E and Z. This is why we can't use cis and trans anymore. That we are about to, in a couple lectures, look at rings and the stereochemistry of rings. And rings also don't freely rotate. So in this cyclohexane ring, there are 2 methyl groups that are both wedges, both on the same side of the ring. Guess what we call that conformation? Cis. That these 2 methyls are cis to each other, as opposed to the other one next to it, where one is behind and one is in the front of the ring. They're on opposite sides of the ring. Yes, you guessed it. We're going to have to use the word trans to describe this stereoisomer from this stereoisomer of the ring. So rings will have stereochemistry as well, and we're going to reserve cis and trans for the rings and use E and Z for the alkenes. Sorry. It's kind of cool. Okay. Rule 2, because we need rule 2. Look how complicated this structure is. Oh my God, it's massive. All right, I want you to just pay attention to this alkene and ask ourselves, is this alkene E or Z? How would we figure that out? We'd go to rule 1, and we still want the group on one side and go off the 2 branches of that alkene carbon, that possible stereocenter, and see if we can generate a point of difference. Because right now, I come off on that far left-hand side, and both are attached to carbons. There's no difference. I'm warning you, please do not just assume that because one is an ethyl and one is a methyl, one's bigger, one's higher priority, one's lower. That might be the case, but oftentimes other atoms sneak in like oxygens and nitrogens, as you can see on the right of those structures. That could change the bulkiness of the group because it's really the atom with the highest atomic number, not the functional group that's the biggest functional group on your molecule. Okay, so we're going to do things and we're going to try to be a little systematic. If these 2 carbons are tied, then what I want you to do from that point is start looking at the 3 bonds attached to that carbon. Excuse me, the 3 atoms attached to that carbon, and label them as such. CHH. I have a C, an H, and an H attached to this carbon, and go down to the bottom carbon and do the exact same thing. And label the 3 atoms and show them on paper, because this is going to be your justification for why you think this is an E or Z alkene. And if you don't do this and you just guess, then you got a 50% shot at getting it right. But then I can't give you any credit at all for partial credit on any answers if you just circled E or Z and you get it wrong. But if you get it wrong now, it's because maybe you just didn't follow one of these 3 dead chemist rules and it tripped you up a little bit, but at least I see you're trying to follow them. So here, first point of difference, I always try to draw the heaviest atomic number atom first, CHH, because then I can look over here and go, yep, carbon is now a bigger atomic number than the hydrogen, which is the biggest one on the bottom, and therefore this group on the top has a higher priority than the group on the bottom, just because it's got a carbon at the next point of difference versus a hydrogen. One little tip, notice I went out to this carbon for my next group. I did not go to the hydrogen. As you'll see in one of these rules coming up, you always want to try to travel down the path that seems to be going to the heaviest atomic numbers. So I would go to the carbon versus the hydrogen because the carbon's heavier. Cool. Systematic. Routine. Let's go look at the carbon on the right of that alkene and see if that's a stereoisomer, a stereocenter. And if I have 2 stereocenters, then this molecule can be E or Z. So do the same thing. Come on out. I see they're both attached to carbons to begin with. So now what are the 3 bonds, excuse me, I always say bonds, the 3 atoms. What are the 3 atoms attached to each of these carbons? In order of highest atomic number to lowest atomic number, I see CCH, and on the bottom carbon, I see CCH. Uh-oh, tied. There is no difference. There is no point of difference at this carbon. So I need to go to the next carbon or the next atom that I think will get me to the highest atomic number. I'm seeing oxygens in one of these chains, so I'm going to go down this path and not do this one to this carbon. Even though they both lead me to a carbon, same thing here. This leads me to a carbon here. So does that one, but I see a bunch of hydrogens and I see this oxygen out here. And maybe that oxygen will play a role in determining the heaviest path. So try to go down the path that leads you to the most atoms, heaviest atoms. But now I went down this path and they both take me to a carbon. If one was an oxygen and one was a carbon, I'd be done, but I'm tied. So according to rule 2, look at the 3 atoms attached to this carbon. Has to be 3 because carbons love to be 4 bonded. So the 3 atoms attached to this one on top, oops, come back. Oh, went too fast. Okay. Okay, the one on the bottom will start, wait, on top. Come on. Here we go. The one on the top is connected to 2 oxygens. Why 2? Because I have 2 bonds coming off that carbon to an oxygen, treated as 2 oxygens. I need 3 atoms total to be written in this parentheses. So this carbon is bonded to a hydrogen and 2 oxygens. The one on the bottom is bonded to an oxygen and 2 hydrogens. So again, I write them in order so I can do point of difference. These 2 cancel each other out, oxygen, oxygen. But then this one is the next highest atomic number on the top, and this one is the next is an H below. So this one is going to be a higher priority, and the bottom one's going to be lower. And now I can see that I have an alkene that has 2 stereocenters because they have differences of the groups coming off. And I think it's just because I love saying same side that I made these Z again. Because I think that's just so cool. Same side. All right. This is a process, not necessarily short, depending on the complexity of your molecule. But be systematic in your approach and you'll be fine in determining E and Z. Last rule, which involves a little craziness, which means I have to give you a molecule that looks a little crazy, like this one. Huge, lots of double bonds everywhere. What I want you to notice, first of all, is this alkene at the bottom here has 2 H's coming off of it, and therefore will never have an E or Z designation given to it. It is not a stereoisomer. Yet the red one is. And let's go through and what I did to help you see this red one and determine high and low is I've color coded all of the atoms. So coming off on the left, I can see that I make 2 carbons, the green and teal one. Okay, so they're tied. So again, now I go out and I start looking at what are the 3 atoms attached to that green one, what are the 3 atoms attached to the teal one, and I write them in order, OHH, CHH. Notice O is better than C, and therefore on this side will be high priority. Whoa. Come on. And this side of the alkene will be low priority. Even though, notice that bottom side has like a benzene ring and a C double bond O and chaos, and the top only has a little OH and a little CH2. It's the fact the proximity of that OH is closer to that red alkene than that benzene ring or that aldehyde way out there, and therefore it's going to cause more issues in steric strain if I were to happen to have a Z, a same side isomer. Okay, I'll try not to say Z as many times. I wonder if this one's Z. So do the same thing on the other side. You can see I've started already. Happy clicker with my pink carbon and my black carbon. These 2 are both carbons. So I started labeling the 3 bonds attached. Notice I have 2 green carbons because it both goes to a green carbon and an H. The black carbon also goes to 2 blue carbons and an H. So they're tied. No difference. Okay? But I'm always labeling and listing 3 bonds total for the carbon. So I'm labeling 3 atoms for every carbon. Go out to the next highest path, which means go through those 2 double bonds and go to the green carbon. And you will see if you go out from the green carbon, you go 1, 2, wait, I only have 2 going out. I need 3. So as you can see, it goes backwards now to the pink carbon. That pi bond going backwards is the 3rd bond that needs to be represented for that green carbon. So it really is a C, H, and the C going backwards to this pink carbon. Very rare, but every atom needs 3 atoms listed for it. So try the same thing for the bottom. The blue carbon down here is bonded to 2 H's going away, and then the black H from behind through the pi bond. So it is a CHH is attached to that blue one. And now I can see a point of difference. It's not the carbon that's attached, it's going back to that carbon or going out to a hydrogen. So this one is high. Oh, I'm so excited. Guess what this one is? Yes? Yes? Say it with me. Same side. Z. Woohoo! Okay, I have a preference for Z. Can you tell? Okay, I'm sorry. I think it's such cool. Same side. Z. So let's see if I have a preference in this question for you. Please answer this and bring it to your study group in class. And most importantly, please don't just circle one of these multiple choice answers. Please come to class with an explanation of why you circled one. Please don't let your lab group or your study group down. They're counting on you. They need you to help them see the light, and whether this is Z or E or cis or trans, and see if we can get nomenclature involved in this process as well. So help each other out. That's the goal of Orgoland. Let's play some more. Here's another practice problem. Oh my God, a big bunch of different alkenes. Please just tell me if this alkene is E or Z, okay? And please make sure to note all the 3 atoms that are attached if they're different and where the point of difference is, and take a picture of it on scratch paper if you need to, or in your PowerPoint blank slides. And I'd love for you to take that picture of your answer to this question and put it in our Jamboard slide, okay? Do not wait for the study group. Post your picture of the answer in our Jamboard slides before class begins. No longer waiting for everybody else to come to your rescue. You are the one that is going to be the master of E and Z, and you are the one that's going to help your group figure it all out. Cool. Why not have one last one? So again, the red one here, there's only one alkene, but this is either E or Z, or as I mentioned in this multiple choice, it is neither. Maybe there is no stereo center on one side or the other, and therefore there'd be no E or Z. Okay? Keep playing with the 3 dead chemist rules. And for our next lecture, it would be awesome if you guys could build with your molecular models and come to watch the lecture with the model of ethane already built, and also be ready to just add 2 more carbons and make it into a butane chain. So next class, next lecture, we are going to look at no more alkenes, but we're going to look at these kind of questions, like why do we always draw these alkane chains as little zigzags and not just lines anywhere? Why zigzag? That's what we're going to do in the next lecture. And then the lecture after that, we are going to look at 6-membered rings. So we got some fun ahead of us with stereochemistry. Keep asking questions. I love your questions. Email me your questions. I'm more than willing to meet with you anytime because I love being in Orgoland, if you can't tell already. Okay. I hope you're doing well. I'll talk to you soon. Bye.